So the next part of the discussion here is conductance of strong and weak electrolytes. Strong and weak electrolytes. If we take conductance of strong and weak electrolytes, here let us try to approach the topic in this pattern. That is, if you go to the conductance, here we mean to say upon increase of dilution, increase in dilution decreases the concentration of electrolyte, and so therefore here you find that there is increase in the molar conductance. You can see that there is increase in the molar conductance and decrease in specific conductance. K stands for specific conductance or conductivity, and lambda of m represents the molar conductance. So if that is the case, actually the conductance, the molar conductance or the conductance of strong electrolytes is actually given by the variation of conductance, with strong electrolytes, variation of conductance with strong electrolytes is actually explained by Debye-Huckel's Onsager's equation. Explained by Debye-Huckel's Onsager's equation. So what is Debye-Huckel's Onsager's equation? That is, molar conductance is equal to equivalent conductance or molar conductance at a given concentration is equal to equivalent conductance at infinite dilution minus of, that is, you can take open the bracket and you can take 82.4 divided by dt base n plus 8.20 into 10 to the power of 5 divided by dt whole to the power of 3 by 2, and this is power of half into equivalent conductance at infinite dilution, close the bracket, into square root of concentration of C. So here if you take this expression, what does this expression actually mean? If you go to this expression, if you go a little bit in detail, or we can write the same expression as okay, first let me try to highlight all the terms here. So this is lambda of m is that is molar conductance at a given concentration, lambda of naught, or you can simply say lambda of infinity at infinite dilution, the equivalent conductance at infinite dilution base of naught, or simply you can take lambda power of infinity. If you take, this is molar conductance at infinite dilution, and here d is the dielectric constant of solvent in electrolytic solution in electrolyte, and of course this symbol is eta. It stands for coefficient of viscosity of electrolyte, and T is the temperature of electrolyte, and C is the concentration of electrolyte. So I'm just trying to, let me put this expression in a much simpler form. I'm going to take this whole term, that is 82.4 divided by d into t, power of half base of, that is eta, plus of 8.20 into 10 to the power of 5 divided by dt power of 3 by 2, this into multiplied with the equivalent conductance at infinite dilution. So this expression I am going to take it in terms of, that is B, where this term, this whole term I will consider it as B, where this P depends on nature of solvent and sometimes even nature of electrolytes. So that means depending upon the nature of solvent and nature of electrolytes. So I will consider this as, this whole term I can consider it as, A, and this whole term I can consider it as B. Then I can take this as, that is B dash. I will take this as B dash, or I can take it as A and C. Here I can take this as C, and this I am going to take it as B, where A and C are the physical constants, Debye-Huckel's physical constants. Here, where in the expression A comma C, therefore A comma C of B are the physical Debye-Huckel's constants. Physical Debye-Huckel's constants. Debye-Huckel's constants, which in turn depends upon nature of solvent and nature of electrolyte, A comma C. So therefore, just I am going to remodify this expression. I will put it in the simpler terms, like molar conductance at a given concentration is equal to molar conductance at infinite dilution. Molar conductance at a given concentration is equal to molar conductance at infinite dilution. This is minus of the whole term, I am going to take it as minus of B into, that is square root of its concentration. So that means now the same Debye-Huckel's Onsager's equation for strong electrolytes, we are writing it in the simpler form of, that is equivalent conductance, molar equivalent conductance at a given concentration is equal to equivalent conductance at infinite dilution minus of the B as a constant, that is Debye-Huckel's constant, into, that is square root of its concentration. So therefore now what is happening here is, convert this into equation of straight line to plot a graph, convert this to equation of straight line, y is equal to mx plus c. So that means it's very clear that once you are obtaining the expression y is equal to mx plus c, to obtain the graph, the slope is negative, the b is going to become the slope, minus of b is going to become the slope. So you get a straight line with a negative slope, and you can see that the equivalent conductance at infinite dilution lambda of naught is extrapolated at the y axis. So let us see what kind of graph we are going to get from this expression. So here if you go to the Debye-Huckel's Onsager's equation for strong electrolytes, once again the molar conductance is equal to, that is equivalent conductance at infinite dilution minus of B into under root of C, where B is a constant, Debye-Huckel's constant, where it depends upon the, that is it depends on the nature of that is the concentration of the solution, and the nature of electrolyte, it depends. So therefore here what is happening here is, we convert this into equation of straight line, mx plus c. If you are going to take, then if you are going to plot the graph here we are finding that in the x axis we are taking root of concentration term, and in the y axis you are taking, that is equivalent conductance, that is molar conductance at a given concentration. Then because the intercept is the equivalent conductance at infinite dilution lambda naught, and the slope is minus of b, so you are going to get a straight line, that is something like this. So here if you take the straight line with a negative slope, so this comes with the, this is for strong electrolytes, this is for strong electrolyte, and this is for weak electrolyte. So this is for weak electrolyte, and you can see the extrapolation is done for the C is the intercept, so extrapolation is done at 0 concentration. So this is the point of extrapolation, where C is equal to lambda of naught. So that means for strong electrolytes, the extrapolation is done at 0 concentration, but for weak electrolytes extrapolation is not possible. That is why what is happening here is, from here From here the conductance of weak electrolytes is actually explained by, it is because of this reason the conductance of weak electrolytes is actually explained by Colrausch law of independent migration of ions. So here with this expression, with the Debye-Huckel's on-cycle equation, the only advantage is we can calculate the molar conductance for strong electrolytes by extrapolating the equivalent conductance of infinite dilution on the y-axis, and we can easily differentiate the strong electrolytes from that of the weak electrolytes. So now the second part of the discussion here is, let us go to that is conductance of weak electrolytes. Conductance of weak electrolytes. If you go for weak electrolytes, if you are going for weak electrolytes, actually the conductance of weak electrolytes was explained by Colrausch law of independent migration of ions. Colrausch law of independent migration of ions. So we can take, suppose if you are taking a weak electrolyte, if you are taking electrolyte, if you take some examples of weak electrolytes, like you can take weak electrolytes, you can take sodium cyanide is a weak electrolyte. Sodium cyanide is a weak electrolyte. Na2CO3 is a weak electrolyte. Sodium phosphate is a weak electrolyte. Then sodium acetate is a weak electrolyte. Then ammonium acetate is a weak electrolyte. Ammonium chloride. All the salts in which, in either of the case, either the acidic or basic part, if it is weak, the overall salt is going to become the weak salt, and weak salts are nothing but weak electrolytes. So all these electrolytes, or suppose if I give you one general formula for the electrolyte as xy, if xy is the weak electrolyte, this xy is subjected to infinite dilution. If it is subjected to infinite dilution, then the equivalent conductance reaches the limiting, it reaches the limiting factor. Then once it reaches the limiting factor, then the equivalent conductance is going to become the infinite dilution, the equivalent conductance at infinite dilution. Once you say equivalent conductance at infinite dilution, that means the concentration is 0. When the concentration is 0, the equivalent conductance is going to become the infinite dilution equivalent conductance. So therefore, if you take this, if you want to put it in the form of Colrausch law of independent migration of ions, that is, if you want to just show the mathematical expression for Colrausch law of independent migration of ions, take the electrolyte, that is xy, which is at infinite dilution. The equivalent conductance of the electrolyte xy at infinite dilution corresponds to, it is going to give the equivalent conductance of the cations at infinite dilution, multiply with the y plus y into the equivalent conductance of cations at infinite dilution plus equivalent conductance of y minus at infinite dilution into x, where x and y are the number of cations which are showing the equivalent conductance, and y is the number of cations at showing the equivalent conductance at infinite dilution, and x is the number of anions which are showing the equivalent conductance at infinite dilution. That means, I mean to say, each and every cation, each and every ion has certain amount of contribution towards the equivalent conductance or the molar conductance at infinite dilution. That means this x and y, that is small x comma small y, we can take it as small x, you can just mark this as like this, small x, and this is small y. If I take the small x comma small y are the number of cations and anions contributing to the conductance, equivalent conductance, contributing to the equivalent conductance at infinite dilution of electrolyte. So if you want to put it in the form of mathematical, if you want to put it in the form of a definition for the Colruy's law, the equivalent conductance of a given electrolyte, the equivalent conductance of a given electrolyte at infinite dilution is always equal to the sum of their individual equivalent conductances of the cations and anions when subjected to their infinite dilution. So that means if you are taking an electrolyte, the equivalent conductance of the electrolyte XY at infinite dilution is equal to the sum of the equivalent conductances of the cations as well as anions at the infinite dilution is nothing but equal to the conductivity shown, the conductivity shown by the weak electrolytes at infinite dilution. So you can see the powers I am very clearly mentioning the infinite dilution. This alpha represents that the electrolyte is always subjected to, already it is subjected to infinite dilution. So therefore their net conductivity, their net molar conductance, or the equivalent conductance at infinite dilution is always equal to their sum. But each cation will have certain number of, each cations have certain amount of cationic groups in the electrolytes and certain amount of anionic groups in the electrolytes. So therefore that is why the equivalent conductances of cations and anions are multiplied with the y and x. Y and x will give you the number of cations and anions contributing to the equivalent conductance of the electrolyte at infinite dilution. So here the applications of, next part of the discussion, applications of Colruy's law of independent migration of ions. Independent migration of ions. Applications. So there are 4 important applications of Colruy's law of independent migration of ions. Number 1, that is calculation of the equivalent conductance at infinite dilution. Calculation of equivalent conductance at infinite dilution. Conductance of weak electrolyte. At infinite dilution. This is the first application, calculation. Second is we can calculate the degree of ionization of weak electrolyte. So we have a formula here. That formula, if you remember, that's more than enough. Degree of ionization of weak electrolyte, that is degree of ionization is given by alpha. Alpha is equal to molar conductance at a given concentration divided by molar conductance at a given concentration divided by molar conductance at infinite dilution. This formula, if you are going to remember, it's more than enough. So here lambda of m at C, power of C, is nothing but molar conductance at concentration C moles per liter. Concentration C moles per liter. Molar conductance, power of alpha means molar conductance at infinite dilution. Alpha is the degree of ionization. Here this alpha represents the degree of ionization. Then third one if you take, we can calculate the solubility of sparingly soluble salts. Solubility of sparingly soluble salts. Actually here what I mean to say is solubility is directly proportional to concentration of electrolyte. When I say concentration of the electrolyte, it can be molarity, or it can be normality. And here this solubility, so therefore slightly I am going to modify the expression here. We already knew that molar conductance is equal to K into 1000 divided by when I say molar conductance, in the denominator we have to divide it with molarity. And here equivalent conductance, lambda of equivalent conductance is equal to K into 1000 divided by N, that is normality. This formula also we know, but because we are considering molarity and normality are equal to solubility, so slightly I am going to remodify this, that is molar conductance is equal to K into 1000 divided by, that is solubility. So therefore, if it is solubility, S is equal to, S represents the solubility term, which is equal to K into 1000 divided by molar conductance at a given concentration. So this is the formula which we are supposed to, use it for the solubility of a given electrolyte. So almost 3 important applications we have done, and we have one more fourth application here in the Colruyt's law of independent migration of ions is calculation of dissociation constant of the dissociation constant of weak electrolyte. So when you are calculating the dissociation constant of weak electrolyte, we can directly apply the formula, that is alpha is equal to, that is K is equal to, that is C into alpha square divided by 1 minus alpha. This formula if you are going to apply, where C is the concentration of the electrolyte, and alpha is the degree of ionization or degree of dissociation of the electrolyte. So by substituting the value of degree of ionization, alpha is equal to the equivalent conductance, the molar equivalent conductance, at a given concentration divided by molar conductance at infinite dilution. This ratio, if you are going to substitute in this expression, we can automatically calculate the dissociation constant of weak electrolytes. So there are 4 important applications for the Colruyt's law of independent migration of ions for weak electrolytes. Those 4 important applications are: first one is calculation of the equivalent conductance or molar conductance at infinite dilution of the weak electrolytes. This is the first application. Second one is degree of ionization of the weak electrolyte, where we can calculate the degree of ionization by taking the formula alpha is equal to equivalent conductance at a given concentration or molar conductance at a given concentration divided by molar conductance at infinite dilution. Then the third application of the Colruyt's law of independent migration of ions, solubility of the sparingly soluble salts, that is solubility is directly proportional to concentration of the electrolyte, molarity and normality. So therefore finally the revised formula for calculating the solubility of the given electrolyte for sparingly soluble salt is equal to, solubility is equal to, that is specific conductance into 1000 divided by the equivalent conductance, that is molar conductance or equivalent conductance. So among these 4 applications, now let us try to reapply the calculation of the equivalent conductance at infinite dilution for a given weak electrolyte. So here if you go to the one of the most important application of the Colruyt's law of independent migration of ions for weak electrolyte. Suppose a question is given to us, say for example, calculate the equivalent conductance at infinite dilution for the weak electrolyte, that is acetic acid, if the data given is, that is CH3 COO of Na, sodium acetate when it is treated with acid, that is aqueous, this is also aqueous. So here it is going to give, it dissociates to give CH3COOH plus, that is NaCl, aqueous. This is also aqueous. So here this is a salt of that is strong base plus weak acid. Salt of strong base plus weak acid, this is strong acid and it is going to give a weak acid, and this is salt of strong acid plus strong base. So this is the area which we are trying to calculate its equivalent conductance at infinite dilution. This is what we are supposed to calculate. So what I am going to do here is slightly let us modify this equation. So first I am going to take it like this: equivalent conductance at infinite dilution of sodium acetate. So suppose if I am taking the equivalent conductance of sodium acetate, the equivalent conductance of sodium acetate at infinite dilution plus the equivalent conductance of HCl at infinite dilution is giving us the equivalent conductance at infinite dilution of acetic acid plus equivalent conductance at infinite dilution of NaCl. So now now that we want to calculate the equivalent conductance of the acetic acid at infinite dilution, so therefore equivalent conductance of acetic acid, next step, equivalent conductance of acetic acid at infinite dilution is equal to equivalent conductance of the sodium acetate at infinite dilution plus equivalent conductance of HCl at infinite dilution minus you get equivalent conductance of the sodium chloride at infinite dilution. So what is the best thing what we can do here is just you can expand this. If you expand this step, then we can calculate the equivalent conductance of the weak electrolyte, that is acetic acid. So let us try to expand this step. So when you are trying to expand this step, the best thing what I can do here is, that is equivalent conductance at infinite dilution of acetate ion plus equivalent conductance of the Na plus ion at infinite dilution plus equivalent conductance of H plus ion at infinite dilution plus equivalent conductance of, that is Cl minus ion at infinite dilution minus, because this is minus sign, so both the equivalent conductances of Na plus and Cl minus should be minus. So therefore equivalent conductance of Na plus at infinite dilution minus equivalent conductance of Cl minus at infinite dilution. So the best thing is the equivalent conductance of Na plus ion, positive term, then the equivalent conductance of Na plus ion, negative term, both have to get cancelled. Then equivalent conductance at infinite dilution of Cl minus ion, positive term and negative term will get cancelled. And now I think it's very clear that from the expression it is very clear for you that we have only the equivalent conductance of acetate ion at the infinite dilution and the equivalent conductance of H plus ion at infinite dilution. So when you sum up these two equivalent conductances, finally you are going to get the equivalent conductance of weak electrolyte, that is acetic acid. So here if you look into the numerical, the molar conductivity of 0.025 moles per liter means here the concentration is given from the data of the problem. The molar conductivity is given as 46.1 Siemens centimeter square of mole inverse. So first I am writing that the molar conductivity at a given concentration, power of C I am taking here, at a given concentration it is given as 46.1 of Siemens centimeter square of mole inverse, and the concentration is given, molarity concentration is given 0.025 moles per liter. I am taking, no problem. Then he is asking us to calculate alpha, so directly I am taking alpha is equal to, I am using the formula, the molar conductance at a given concentration divided by molar conductance at infinite dilution if I take. So this I can take it as molar conductance at a given concentration is 0.025 molar, so directly I am going to substitute 0.025, but molar conductance at infinite dilution is given by molar conductance at infinite dilution of H plus ion plus molar conductance at infinite dilution of formate ion. If you take, then this value is going to become, that is 0.025 divided by the molar conductance of H plus ion is, that is we can take 349.6 plus the molar conductance at a given concentration at infinite dilution is given by 54.6, then this value is going to become 0.025 divided by, so this upon simplification 349.6 and 54.6 if you take, this is 12 1 10 14 and 1 this is 10, so this is going to become 404 point, so this is 12 1, this is 10 14 14, that is 9 10, so 404.2. So 404.2 upon simplification you are going to get 0.114 is the final value which you are going to get upon simplification. So the alpha value we got, that is the degree of ionization value, you got it as 0.114. Now again, because it is asking us to calculate the dissociation constant, so dissociation constant means, what is the concept here? Calculation of the next part of the discussion, that is calculation, next part of the numerical, calculation of dissociation constant. Calculation of dissociation constant means, because formic acid is already an acid, so formic acid is an acid, so because it is an acid, dissociation constant, if you take, so I can take this as, take the formic acid in the aqueous state, it dissociates to give one formic ion, one formate ion and one H plus ion. Initially, let us suppose that initial concentration is C moles per liter. So because it is undergoing certain amount of dissociation, initially let the concentration of the formate ion and let the concentration of the, the formate ion and the proton be 0, but after certain amount of time, at equilibrium, or you can say at equilibrium, the how much amount of the concentration of the formic acid has been ionized or dissociated into formate ion means C into alpha, and this is also C into alpha. So this is C minus C alpha is the remaining concentration. So this we can write it as C into C minus C alpha, or you can simply write this as C of 1 minus alpha. So applying the equilibrium constant expression, so you can take Ka is the dissociation constant of the weak acid, formic acid, which is equal to product of the concentration of the formate ions into concentration of H plus ion divided by the concentration of formic acid. If you take, so this upon simplification, that is C into alpha divided by C of 1 minus alpha, if you take, so this expression is going to become C, and concentration term in the numerator gets cancelled, C into alpha square divided by C of 1 minus alpha. So here substitute the value, the concentration already we know, that is 0.025, so 0.025 into the alpha value also we know, this is 0.114 whole square divided by, this is going to be 1 minus 0.114, so Ka value is going to become 3.67 into 10 to the power of minus 4 moles per liter is the final answer for the problem. So we have successfully calculated the dissociation constant is going to become Ka, and the degree of ionization, that is alpha, is nothing but the degree of ionization in the problem. So in both cases we have calculated the value successfully. So here the next part of the discussion is, that is laws of electrolysis. Otherwise we can also call it as Faraday's laws. Actually the process of electrolysis is governed by electrolysis is governed by Faraday's laws. Faraday's laws. So here in this we have the first one, that is Faraday's first law. If you take, so here if you take the Faraday's first law, suppose if I am taking, because the process is electrolysis and this electrolysis process is being explained by the Faraday's first law. So the best thing what I can do here is take one electrolytic cell. This is the electrolytic cell. Fill it with the electrolyte. This is the electrolyte. You can take any damn electrolyte, copper sulfate, silver nitrate. You can even take acids also. Acids, bases, salts, all are electrolytes only. So you can take any one of the electrolytes from the different category. But in the meantime, suppose if I am taking, for example, if I am taking say an electrode. Here I am taking two electrodes. One electrode will behave as anode and the other electrode will behave as cathode, and that is positive terminal and negative terminal. This is battery, and here you can see that there is a power key. This is key. So this is a simple electrolyte. This is electrolyte. Electrolyte you can take, and here you can see that this is acting as cathode electrode. Cathode, this is platinum electrode, this is also platinum electrode, inert electrodes you can take, and this is cathode electrode, which is given the sign convention, negative sign convention, and this is anode electrode, which is given the positive sign convention. So you can see that here this is the power source. This is the power source, that is battery, and this is key. So the current flows from the anode to cathode. This is the flow of current, and this is electrolytic cell. Electrolytic cell or voltmeter, or sometimes we also call this as coulometer. Different names are given: electrolytic vessel or electrolytic cell, voltmeter or coulometer, whatever, fine. So here the electrolyte is NaCl. Suppose if I am taking NaCl that is fused or aqueous, you can take any one of the electrolyte, but one thing what you have to understand here is, whenever you say if the metal is deposited, always during the electrolysis metals are deposited. Metals are always deposited. The terminology what we have to use in electrolysis is metals are always deposited. The deposition always takes place at cathode. It can take place at cathode or anode. There is no condition that they have to always deposit at cathode or anode. Again, non-metals if you take, they are liberated maybe at cathode or anode. So that's why we simply say, that's why when we are trying to classify the non-metals and metals using the term deposited or liberated, we simply say electrode deposition or liberation. We don't mention in definition, that's why, which is metal and which is non-metal. So therefore, if you go for Faraday's first law, you can define it like this. That is, the amount of statement of Faraday's first law, amount of substance deposited or liberated, amount of substance deposited or liberated at electrodes. Electrodes is directly proportional to quantity of electricity passed into electrolytic solution. So mathematically, when you are trying to write it in the form of mathematical expression, this statement directly proportional to quantity of electricity passed into the electrolytic solution. So this is the statement. So mathematically, how do you understand here? So when you go for mathematical expression, the amount means you can take amount means here you can take W or M. You can use two different terms. Either you can use W or you can use M. Both mean one and the same here. You can express W in grams, mass also in grams. So the amount of substance means what I am doing here is W is the amount of substance deposited or liberated at an electrode, is directly proportional to, when I say quantity of electricity, that quantity of electricity is given by Q. So if I remove the proportionality, I am going to get a constant, that is Z into Q, and if I expand this Q, of course here where Z is a constant called electrochemical equivalent. Electrochemical equivalent, and which depends on the nature of electrolyte, which we are using in the electrolytic cell, and also the nature of electrodes which we are trying to use in the electrolytic cell. The Z depends on electrolyte in the vessel, and also it depends upon the nature of electrodes which we are trying to use. So therefore, again if you expand this Q, W is equal to Z into, that is Q is nothing but quantity of electricity, which is equal to the product of current into time. So this is the actual expanded form of the Faraday's first law, and where here I represents the strength of current. Which is passed into the electrolytic solution, and T is the passage of time. So this is the simplest expanded form of the Faraday's first law. W is equal to Z into I into T. So therefore, suppose for example if I am taking Z is equal to W by Q, that means it is very clear that the Z value is going to become equal to 1. That is, when 1 coulomb of electricity, when a current of 1 ampere with the time of 1 second, if it is going to, when the current of 1 ampere in 1 second, if it is going to be passed into the electrolytic solution whose weight is 1 gram, then the electrochemical equivalent of that electrolyte is going to become equal to 1 gram per ampere into second, or simply you can take Z is equal to gram per coulomb, because charge is expressed in units coulombs. So either you can take gram per coulomb as a unit, or you can take gram per ampere second also as a unit for the electrochemical equivalent. And the electrochemical equivalent for a given electrolytic solution depends upon the nature of electrolyte and also the kind of electrodes which we are trying to use. So this comes under the Faraday's first law. So now let us go to expanded formula of Faraday's first law. If you go for the expanded formula of the Faraday's first law, now you know that the simplest formula for the Faraday's first law is W is equal to Z into, that is I into T. You can take where I is the strength of the current and T is the passage of time. And so now I am trying to expand this Z here. W is equal to E by F into I into T. That means the electrochemical equivalent of the electrolytic cell is equal to, that is capital E divided by F, since the electrochemical equivalent is equal to capital E divided by F, where E is called chemical equivalent. Chemical equivalent is different and electrochemical equivalent is different, mind you. Chemical equivalent, E is the chemical equivalent of electrolyte, E is the chemical equivalent of electrolyte, and F is the Faraday's constant. Faraday's constant. What is this Faraday's constant all about? Actually, to carry the electricity, to carry the electrolytic process in an electrolytic cell, to carry the electrolytic process, we need to always supply certain amount of electricity into the electrolytic solution. So if 1 mole of electrolyte, that means if 1 mole of electron is being passed into electrolytic solution in the form of electricity. This 1 mole of electron means you are nothing but we are trying to send certain amount of electricity, because flow of electrons is nothing but current. Flow of electrons is nothing but current, and that current is being sent in the form of quantity of electricity. So therefore, if you are passing 1 mole of electrons into the electrolytic solution in the form of electricity during the process of electrolysis, then 1 mole of electron means At STP, 1 mole of any substance, maybe a particle, substance, molecule, atom, anything you take, it contains equivalent to its Avogadro's constant. So 1 mole means, first let us take the charge of electron. The charge of electron is 1.6 into 10 to the power of minus 19 is the charge of the electron, but charge is always expressed in coulombs. So 1.6 into 10 to the power of minus 19 coulombs multiplied, this is the charge of electron, mind you, this is the charge of electron, and 1 mole of the electron means you have to multiply it with 6.023 into 10 to the power of 23 electrons. 1 mole of electron means multiplied with 6.023, so this is going to become, this is nothing but 1.6 into 6.023 into 10 to the power of 23 into 10 to the power of minus 19. This upon simplification you get 96,500 approx. I am taking, you are not going to get exact value which is equal to 96,500 coulombs, but nearly you are going to get 96,500 coulombs, which is equal to 1 Faraday of electricity. So therefore we can come to one conclusion that always 1 Faraday is equal to 96,500 coulombs. It's a constant value. So this we have to keep it in mind. Or 1 Faraday, shortcut you can also write this as 1 Faraday is equal to E with negative charge into N naught. Because when you substitute the value of electronic charge of electron equal to 1.6 into 10 to the power of minus 19 coulombs, and if you multiply it with Avogadro's constant, then only you are getting this value equal to 96,500 coulombs. So that means now we have a clear picture of the Faraday's constant in the first law of the Faraday during the electrolysis. Then still we can expand. So take this expression, I'll put this in box. Take this expression, from this expression I want to go for one more expansion. W is equal to, that is m by n into 1 by f into I into t. One more expansion I am making. This is because, what I can say is, this is because capital E is equal to m by n. So m is nothing but the atomic weight of species, sometimes even molecular weight also you can take, atomic weight of molecular weight of the species. N is the valency of species. When I say species in the electrolysis, the species can be cationic or it can be anionic. So this is the complete expanded formula. This is the complete expanded formula of the Faraday's first law. So F we know, I we know, T we know, N we know, M we know. So with this formula we can calculate any kind of numerical problem which is given to us in the case of Faraday's first law. So here if you look into this problem, a current of 0.5 amperes flows through a metallic wire for 2 hours, then how many electrons will flow through the conducting wire? Suppose that means if this is the conducting wire, so this is the conducting wire and we are trying to pass a current equal to, that is 2 amperes, sorry not 2 amperes, it is 0.5 amperes, 0.5 amps of current is flowing through it for a period of time is equal to 2 hours. 2 hours means 2 into 60 seconds. Then and there we are trying to simplify. So what is happening here is, because it is asking us to calculate how many electrons, the best thing what we can do is, the quantity of electricity passed through the conducting wire is given by the formula, that is Q is equal to I into T. So I is 0.5 amperes into time is 3600, because 2 into 3600 into 2 if I take, so this is 0.5 into 2 is nothing but 1 only, 1 into 3600. So this is going to become 3600 coulombs, because the charge is expressed in coulombs. But we also know that, since we know now Q is equal to 3600 coulombs we got, so now we know that here if you are taking at STP for every 96,500 coulombs of charge, 6.023 into 10 to the power of 23 electrons will flow in a conducting wire. This is a sequence which we have to follow. For every 96,500 coulombs of electricity which we are passing into the metallic conducting wire, the number of electrons equivalent to Avogadro's number of electrons will flow through the conducting wire. But now we got only 3600 coulombs, so 3600 coulombs therefore will produce how many number of flow of electrons are possible in the metallic conducting wire. So therefore this step is going to become, that is 3600 into 6.023 into 10 to the power of 23 divided by 96,500 if you take. So these two zeros gets cancelled. 36 divided by 965 into, I am going to approximate this 6.023 as 6 into 10 to the power of 23 if I take. So this is going to become, that is this is going to become 6 6 is 36, this is 3, 18, 19, 20, 21. So 216 divided by 965 into 10 to the power of 23. So that means this value you can convert this to 2160 divided by 965 into 10 to the power of 22 if you make out. So this is going to become 216 means, I think 965 into 4 times if you take, no, 4 is not possible. If you take 3 also, 9 is 27, it's not possible. If you take 2, then this is 10, 12, 13, 1, 18, 19, 1930 we are getting. So roughly 2 times it is going to, we are going to get into 10 to the power of 22 electrons will flow into the conducting wire. So here that is 2.246. Upon simplification of this step, 2.246 into 10 to the power of 22 electrons will flow through the conducting wire by passing 36 coulombs of 3600 coulombs of electricity. If you are going to pass 2.246 into 10 to the power of 22 electrons will flow through that conducting wire, and that is what we are trying to calculate here, that is number of electrons flowing through the wire. So what is the quantity of electricity, needed for 1 mole of dichromate ion in acidic media? That means, because he is saying he is using the word acidic media, we need to solve this equation. In acidic media, this dichromate ion Cr2O72 minus this dichromate ion, it gets reduced to chromic ion Cr3 plus. Balance the equation in acidic media. If you want to balance the equation in acidic media, there are 2 chromiums, so multiply this with 2. Number of chromiums are balanced. There are 7 oxygens, so that's why to the side, wherever the number of oxygens are less, you add that many number of water molecules. Add 7 H2O, you have 14 hydrogens, so add 14 H plus ions, then check out the charges. If you want to balance the charges, this is reduction half reaction, this is, so because it is reduction half reaction, we need to add the electrons on the reactant side. So therefore the entire reaction has been balanced, and we are able to find that this is nothing but, this is dichromate ion, this is dichromate ion, and this is chromic ion, and this is reduction half cell reaction. So you are finding that the number of electrons involved are 6 electrons. So simply I am going to take one step. 1 mole of dichromate ion is consuming 6 electrons. So number of electrons is equal to number of farads. So that means if 1 mole of dichromate ion is consuming 6 electrons, it also means that 6 Faraday of electricity is required during the process of electrolysis, because 1 electron is equal to 1 Faraday. 1 electron consumes 1 Faraday of electricity during the electrolytic process. So therefore 6 farads of electricity is required. So therefore 6 into 96,500 coulombs of electricity is altogether required. So therefore this is 6 into 965 into 10 to the power of 2 coulombs of electricity. So this is nothing but 965 into 6, if you take 33, 12 plus 3, 15 means 9 5s are 45, 9 6 are 54, 54 if you take, yeah, 9 6 are 54, 55 if you take, so 33, 36 plus, sorry, this is 33, 36 plus 3, 9, 39, this is 3, so 3 if you take, 9 6 are 54, 54 plus 3, 57, so 57, 33, 39, 3, 9 6 are 54, 54 plus 3, 57, okay, so this is going to become, that is 5790 into 10 to the power of 2, or else if I am going to take 5.790 into, because I have shifted the decimal to the 3 units left side, I can take this as 5.79 into 10 to the power of 5 coulombs I can take, or else finally this is nearly equivalent to, that is 5.7 means I will take 6 into 10 to the power of 5 coulombs of electricity is altogether required. So now let us go to the Faraday's second law. Faraday's second law, if you take, let me put the statement first, same amount of current when same amount of current is passed through various electrolytic cells connected in series, various electrolytic cells in same time connected in series, amount of substance deposited or liberated, is directly proportional to their chemical equivalence. Is directly proportional to their chemical equivalence. When same amount of current is passed through various electrolytic cells in same time connected in series, the amount of substance deposited or liberated at an electrode, is directly proportional to their chemical equivalent. So suppose, for example, if I am taking amount of substance deposited at an electrode when same amount of current is passed through various electrolytic cells connected in series is directly proportional to chemical equivalence, means I am taking capital E. When I am removing this proportionality, I am going to get here Z into E, where Z is the electrochemical equivalent. So this also means that Z is equal to W by E, or you can simply say that is W by E is always kept constant. So that means when you are taking group of electrolytic cells connected in series for the Faraday's second law, so the weights can be W1 by E1 is equal to W2 by E2 is equal to W3 by E3 and so on. Wn by En times of the cells can be connected in series. So for example, if I am taking two electrolytic cells like this, for an illustrative purpose, if I am taking two electrolytic cells like this and I am trying to place two electrodes, one electrode I am placing here, pair of electrodes here, also pair of electrodes I am taking, and here I am taking they are connected in series. Here I am taking copper sulfate and here I am taking silver nitrate. So here again both these are interconnected with each other, and this is connected to the battery. So I can take here this as positive terminal, this is negative, again this is positive and this is negative. So that means this is cathode electrode and this is anode, again this is cathode and this is anode electrode. So the current passes from the positive end to the negative end. So what is happening here is, like, because you are finding that in the first electrolytic cells, this is the first electrolytic cell and this is the second electrolytic cell which is connected in series. So suppose a question is given to us, like, what is the, from the copper sulfate and silver nitrate, this copper sulfate in the first electrolytic cell, it dissociates to give copper sulfate. Upon dissociation it gives one cupric ion aqueous plus sulfate ion aqueous, and silver nitrate also AgNO3 of aqueous, reversible reaction Ag plus of aqueous cation plus nitrate of aqueous anion. So what is the relative ratio, what are the products obtained, what is the ratio of, question is ratio of metals deposited ratio of the metals deposited at electrodes, ratio of weights of metals deposited at electrodes when they are connected in series. When connected in series is the question. So how do you answer this question? So what we are noticing here is, this is a cation at the cathode and cupric ion at the cathode and silver ion again at the cathode. So both copper and silver, both of them, they get reduced at the cathode electrode, and so therefore directly we already know that W by E is equal to constant. So this we can slightly modify, that is weight of copper divided by equivalent weight of copper is equal to weight of silver divided by equivalent weight of silver. So copper is bivalent here, so if you want to calculate the equivalent weight of copper, so equivalent weight of copper is given by, that is equivalent weight of copper, it is given by atomic weight divided by valency. So 63.5 is the atomic weight of copper, valency is 2, so that's why 63.5 divided by 2 is the chemical equivalent of copper. And if you go for silver, equivalent weight of silver is equal to, that is atomic weight of silver is 108, valency of silver is 1. So substitute these two values in the expression. So weight of copper divided by weight of silver is equal to, that is equivalent weight of copper divided by equivalent weight of silver, which is equal to, that is copper is 63.5 divided by 2 into 1 by, that is equivalent weight of silver is 108. So therefore this step upon simplification you can take, that is weight of copper divided by weight of silver is equal to 63.5 divided by 2 means you can take this as, that is 63.5 divided by 2 means this you can take it as 31, 3, 1, 15 means 7, 63.5 by 2 means 2 ones are 3s are 1s are, again 1 means 7, 5, so 31.75. So 31.75 divided by, that is 108. So 108 means nearly I will take this as 32 by 108 nearly. So if 32 by 108 means 32 into 4 times, no we can't take, 32 into 3, 6, 9 we can take. So nearly, so 32 means like 108 of 32, 3 means you can take 3s are 96. So this is 2, 1.0. So 108 means almost you can take again 3 times only, so 3.3s are. So roughly I'll take it as 3. So therefore the ratio is, so weight of copper is to weight of silver, weight of copper is to weight of silver is equal to, that is 1:3 is the answer. So here if you go to the next part of the discussion, that is mechanism of electrolysis. In this mechanism of electrolysis, product of electrolysis, product of electrolysis. If you go for product of electrolysis, actually electrolysis involves electrodes. Electrolysis involves electrodes. These electrodes, they are made up of, that is made up of anode electrode, which is given a positive sign convention, and we have a cathode electrode which is given a negative sign convention. At anode, oxidation takes place at anode, and at cathode reduction takes place. So this is here at oxidation, it is de-electronation. Oxidation involves de-electronation, and reduction involves electronation. Here, when you are speaking about electrodes, electrodes are of two types. One is active electrodes, and here inert electrodes. So what we are noticing here is, generally inert electrodes are particularly used in the case of electrolysis. If the process is electrolysis, then we usually use the inert electrodes only. But if the process is electrochemical process, then we usually use active electrodes. That already we have done in the electrochemical process. That is, for example, if you are taking zinc sulfate, as an electrolyte, and if you are using zinc electrode, then you find that here this is acting as anode. This is anode electrode. This is zinc. No doubt this is zinc electrode, and this is anode electrode, and the current flows from the anode, and you find that there's a melt in the plate, zinc plate. You can see that there's a decrease in the mass. This is called this zinc. That means when there's a decrease in the mass of the plate of zinc electrode, you find that zinc ions goes into the solution. That means indirectly what I mean to say is that whenever you speak about the active electrodes, they involve in electrode reaction either by discharging or depositing. When there is discharging, you find that there is decrease in mass. There is a decrease in mass. And when there is a depositing, there is increase in mass. That is what we have to keep it in mind. And in the case of electrolytic process, during the electrolysis, whether the electrolyte is fused or aqueous, in both the cases the electrode can be inert electrode. For example, if you take fused, means NaCl fused, you take yes, you have anode and cathode both as platinum electrodes, and aqueous NaCl also, NaCl aqueous also, you find that the electrode is again the platinum electrodes only acting as anode and cathode. Say for example, if you take NaCl, you're carrying out the process of NaCl using an electrolytic cell. This is the brine solution, because NaCl is aqueous NaCl is the brine solution. So if I am taking here, one is platinum electrode which is acting as anode, another one is take another electrode. If you take one platinum electrode which is acting as anode and another platinum electrode that is cathode, both are connected to the battery, external battery power source. So here the electrolyte is NaCl. So you can take NaCl fused or you can take NaCl aqueous. It all depends on what kind of electrolyte you are using. So NaCl aqueous, but the reactions are different. So suppose during the electrolysis, if you are taking the electrolyte NaCl fused and NaCl aqueous, if you are using, then anode and cathode, that is anode and cathode, what are the products obtained? Here also again anode and cathode, what are the products obtained? If you go for NaCl fused, yes, at anode we get chlorine gas, and here at cathode we get sodium metal deposited. Again in the case of aqueous, yes, at anode it's not chlorine gas, we get H2 gas, and at cathode we get, that is at cathode we are going to get, that is NaOH, here I think we get anode, no? So here you get O2 gas at anode, and here you get H2 gas along with, that is NaOH. Why? What is the reason? Because what is happening here is, in the NaCl aqueous, along with NaCl we have NaCl mixed with water. So water is acting as a solvent here. So even water will get ionized and NaCl will get ionized. So there is a competition occurring between, in this case there is a competition going on. Here there is a competition. There is a competition between Na plus, Cl minus and H plus and NaCl, Cl minus and even water. There is a competition going on between these three species, and because of that reason we can say that here there is a difference in the products, that is we get at anode we get O2 gas and at cathode we get H2 gas as well as NaOH gas. But for example here in the case of fused NaCl, fused brine solution, you have only one kind of, you get only one kind of Na plus ion, that is sodium. So this sodium ion gets reduced at the cathode to give sodium, and chloride ion gets oxidized at the anode to give chlorine gas. So this is one small difference which you have to make out in the case of electrolysis between the fused electrolyte as well as the aqueous electrolyte, and the principle is same. You take any damn aqueous electrolyte, take potassium chloride aqueous, the mechanism is same. Potassium sulfate aqueous, mechanism is same. You always find different products for the aqueous electrolyte as well as the fused electrolytes.